Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have made quite a bit of progress in this course and we have reached and formulated the renormalization group in the last lecture. So let's just quickly begin by recapping the idea of the renormalization group. So the puzzles, as we all know now, is the origin of universality and the fact that there are scaling laws between different universality classes. And Wilson observed that this whole story can be explained by making a very important hypothesis, or if you wish, elevating it to the level of a law or a principle, is that the system at a critical point has an emergent symmetry. And this symmetry is scale invariance or dilatation invariance. And as we saw in the last lecture, this single principle suffices to sort of find the underpinnings of all the points like universality and scaling laws and such. So what is this scale invariance? The scale invariance requires that we have an arena transformation. This is called as the scale transformations. And under this transformation, the coordinate transforms to a new value by some scale factor. And associated with this arena transformation, we have to also transform the Hamiltonian or the action, depending on the kind of problem you are dealing with. And the way we thought about this is that a Hamiltonian or an action is specified by a set of dimensionless coupling constants. They may not be dimensionless, but it's generically dimensionless. They could be specified by a set of parameters. And this set of parameters can be thought of as a point in the space of theories. And the scale transformation will change the values of these parameters in the sense that you will get a new Hamiltonian with the same form as before, but with different coefficients for the different operators, as we saw in the last lecture. And this transformation taking this point P in the space of theories to another point P is called as the renormalization group transformation. So the way we visualize this is that this renormalization group transformation induces a flow in the space of theories. So if you allow S to vary from some number greater than 1, keep on increasing S, then this point that you started off with P will flow and it will trace out a trajectory in the space of theories, and this is what we call as P of S. So this describes a curve in the space of theories. And starting from every point you can generate a curve, and that's why you get a flow. That's why you think of it as a flow. So within this framework, we also have a way of characterizing our critical points as fixed points of the renormalization group transformation. So fixed point of the renormalization group transformation, if you act the renormalization group operation on the parameter P star, it will remain unchanged, and that's why it's called a fixed point. And this must be true for all values of S, right? And we'll be particularly interested in values of S greater than 1 because from our perspective, we are interested in coarse graining. Okay. Then we went on to say that near a critical point, if you look at points close to the critical point and you apply this normalization group transformation RS on those points, you can characterize this by a linearized version of this renormalization group transformation, which is a matrix called LS. So this matrix depends parametrically on S, and it is actually a property of the properties of the matrix, its eigenvalues, etc., are determined by what critical point you are near. And so this RS of P for a point which is in the neighborhood of P star can be written in this fashion. And what we concluded in the last lecture was that all the properties of the critical points, namely the critical exponents and all of the universal properties, are characterized by the properties of this matrix. In particular, this matrix LS of P star has right eigenvectors and eigenvalues. In fact, we call them eigenoperators, and they satisfy the following eigenvalue equation. Ls of P star acting on this eigen operator OI will be S is the scale factor to the power mu I times OI. So S to the power mu I is the eigenvalue, and this eigenvalue is characterized by this exponent mu I. So you tell me all the operators near a critical point, the eigenoperators of Ls star, and you tell me the mu i's corresponding to that. I can tell you all the universal properties of the critical point. So these operators OI are classified as three types. So they're called relevant operators, and those relevant operators, their eigenvalue or this exponent mu I are greater than 0. So what happens is, as you coarse grain, the coefficients of these operators will start to grow. So we just say that these operators grow on coarse graining. On the other hand, you can have operators whose exponent mu I, eigenvalue exponent, are less than 0, and what happens as you coarse grain is that their strength or the coefficient multiplying these operators, they will go down to 0. So they will die. And there are a bunch of operators, there could be a bunch of operators called marginal operators, for whom the eigenvalues exponent mu I is 0, which means that these operators don't change, the coefficients don't change as you do the scale transformation. So to understand universality, it is enough to observe that around most critical points that we study, there are only a few relevant operators, in the sense that as you go towards the critical point, all physics is determined by a few quantities and all the microscopic details involved are forgotten. Forgotten because they will be put into the irrelevant operators, and as you get closer and closer to the critical point, in another way of saying this is that as you do scale transformation, as S runs larger and larger, those operators, their coefficients will die, and so the physics will be governed by only the relevant operators. Okay. Based on this whole framework, we can deduce that the free energy of our system is a generalized homogeneous function of these few relevant operators. And immediately from this, once we have realized that the free energy is coming out as a generalized homogeneous function, we can deduce all the scaling laws, because the fact that the free energy was a generalized homogeneous function was taken as a hypothesis to derive the scaling laws. But now, just from the fact that the system has scale invariance at the critical point, we are able to derive that the free energy is a generalized homogeneous function, and hence conclude that the scaling laws have to be true. Okay. So all this was assuming that somebody gave us a way to calculate Rs, and from that calculation we were able to obtain these mu i's. But the point is, we have not seen a concrete example of how to construct Rs, and we are quite far away from computing mu i's at this stage. So question is, how do we implement this Rs? In particular, how do we find this flow in the space of theories? And often this problem is also cast in a different way, and we will see later, we'll use this language more frequently later. Rs can be expressed via a differential equation. So what you do is, you look at the derivative of this point Ps, so it is taken as a log derivative, so that's why S d by ds, and this will turn out to be in a sense some kind of tangent vector to this this curve, and that tangent vector is called beta of P, and please do not confuse beta with inverse temperature. This is the convention in the field. So this tangent vector is called as beta of P, and this is called as the beta function. So if you read papers and literature associated with this, they will say that they are interested in computing the beta function of the problem, which means that they are interested in finding the renormalization group flow, which is characterized in this way by finding the differential form of this Rs transformation. So naturally, if you want a critical point, you want to set beta of p star equal to 0. So in fact, if you find this differential equation, you will see that setting the beta of p star equal to 0 and solving the all possible values of p star that is true will give you essentially all the fixed points of the renormalization group. Okay, so this is pretty much what we had seen in the last lecture, and the natural question is, how do we implement this RS? Okay, so there are several methods that have been developed over a period of many decades. So the early methods were what are called real space methods, and the names that are associated with this real space method are Kadanoff and Migdal, etc. And this method works in the real space arena and typically on a lattice. The advantage of this real space method is that it is physically transparent, as you will see, and it is intuitive. You can feel the calculations being done in a physical way. The disadvantage is that it's not a generic method, and every time you encounter a problem, you have to develop a certain technique for performing this sort of real space methods, and many times you end up having to make certain uncontrolled approximations, in the sense that you have to make approximations that you're not sure how to evaluate them quantitatively. Okay. The second method is called as momentum space methods, and this is typically credited to Wilson, who was one of the key formulators of the modern version of renormalization group. And the idea would be to start from a field theory like framework, such as the Owen-Ginsburg-Landau theory, which we have worked on, and work in the momentum space. So you take the fields and you Fourier transform them and work in the momentum space. Okay, we'll see quite a bit of this later in the course. The advantage is that it's a general framework, so you can apply this to a variety of field theories, and you can address a large class of problems with this Wilsonian framework. And the disadvantage, at least from the perspective of a student picking up the subject, is that this requires a fairly well developed set of tools, typically from field theory. And apart from that, there are also other disadvantages, in the sense that most of these methods are calculations are done perturbatively, and although you have some formally controllable expansions and tools of that kind, it's not without problems of approximations and so on. Okay. Finally, there are lots of numerical methods around now, which we will certainly not have time to discuss in this course. But the idea would be to perform the renormalization group calculations on the computer. In fact, I must mention here that Wilson himself was one of the first pioneers of this numerical renormalization group method, and he was able to tackle this very famous Kondo problem with this numerical method. So the advantage is that one can get numerically exact results, in the sense that you give me, if you have enough computational resource, then of course you can get as accurate results as you want. But the point is that you have to have enough computational resource, and the idea is that your formulation is also case by case basis. You have to look at problems and then you have to formulate the correct numerical method for that given problem, and typically you require significant computational resources to give accuracies beyond say some of these other approximate methods. So these are some of the methods of implementing RS that are available in the market. So what we will do in this lecture is we will focus on real space methods, and our strategy is going to be the following. We are going to start with a problem for which we know the full solution, and then we are going to use the real space method or this normalization group method, and we are going to rederive all those calculations by the renormalization group method. So what's the advantage of this? The first advantage is, of course, we are standing on firm ground, in the sense that we know the exact solution of the problem. And second is, we will be able to see the renormalization group in action and obtain the results which we know otherwise to be exact, or for which we know the exact answers. And so we will be able to compare our renormalization group approach with the exact result, and we can see how well or how poorly or whatever, whichever way it performs. So this is our plan. So let's push on. So the natural problem for which we should apply renormalization group is the 1D Ising chain. And the great advantage of this, of course, is that we know the exact solution to this problem. So what is the one-dimensional Ising chain? So here I have to immediately depart from the previous discussions that we had. In most of our previous discussions, we put the one-dimensional Ising chain in a periodic box with n sites, and we did the calculations, and then we took the thermodynamic limit. But as you can imagine, in the renormalization group, you have to start with the infinite system, because otherwise if you rescale the system, becomes smaller and smaller, and it's not going to, it will not help you, and you need the infinite system to see the non-analyticity of the free energy. So what we're going to do is, we're going to start with an infinite 1D Ising chain. So that's why these dashes are there on both sides. So the sites are labeled by I, and the spin at site I is Si, and these arrows are simply random visual things to tell you that there are spins on these sites. That's it. Okay. And the lattice parameter, which is a length scale, which has dimensionful, it has dimensions of length, is this A. Okay. All right. Now I start with this, and the configuration of the spins C is given by some snapshot of all the spin values on all the sites. So that's what the configuration is, and I have to give you a Hamiltonian associated with this. Now already I'm going to choose a dimensionless Hamiltonian, and what I'm going to say is that I have H of C is minus K, and K should be thought of as the exchange coupling, nearest neighbor exchange coupling by temperature, and H, we used to call H as the physical magnetic field, which in our language has dimensions of energy. Here H is already the physical magnetic field divided by temperature, so it is dimensionless already. Okay. And for reasons that will become clear to you as we go along, I also need to tag along some constant energy, right? So that is that associated with each spin, I'm just saying that there is some constant energy which is E0. This appears trivially, if you do a finite system, it appears as trivially a shift of energy, and therefore it should not affect any physics, and it will not affect any physics, but we need it, as you will see. As we perform calculations, you will see that such a term is necessary. Okay, so E naught is also dimensionless because I have divided everything by temperature, so to speak, and so H of C is now a dimensionless Hamiltonian. Okay. So the remarkable thing, of course, is that we know the exact solution of this problem, and the crux of the exact solution can be cast by this first statement, that there is no finite temperature phase transition in this system, right? So this is something that we discovered quite early on in the course. The second statement is that we know that if you perform the symmetry breaking field plus thermodynamic limit, etc., that framework, you can get a broken symmetry state at 0 temperature, and in this language this K will go to 0 as you approach 0 temperature. At any finite K, we have an emergent length scale which we call as the correlation length, please recall this, and this C, correlation length, is A divided by logarithm of cotangent hyperbolic K, hyperbolic cotangent K. So you can see that as K goes to 0, which is at 0 temperature, this will go to 0, and correlation length will go to 0, and as K goes to infinity, this will go to infinity. Okay. So this is the result that we know. Okay. So with this background, I am going to introduce a framework to construct RS for the 1D chain. So what would be a strategy? So I want to perform scale transformation. So the first observation is that I have a lattice. So I cannot I cannot choose scale as scale transformation has to be pi. So I will, if I do that, then I will find it difficult to implement the transformation. So I should first attempt to implement the transformation with some value of s is something like 2. Why 2? If it is 2, then what I could do is I could try to sort of, I have a bunch of spins and I could try to remove some spins by integrating them out, and you will see what that means, and that's what we mean by this decimation. Decimation means killing or integrating out or something, right? And what we will do is we will take the chain and we will organize the sites into even sites and odd sites. So in a sense, we'll double the unit cell of the chain. So in each unit cell, I'll have an even site and an odd site, and I will integrate out the odd spins, and it will become clear to you what I mean by integrate out as we go along. And what I'm hoping is once I integrate out these odd spins, I will be left out with these even spins, and I'll get a new effective Hamiltonian for these even spins. And the hope, which we will see how well it is going to work, is that the new effective action is also a nearest neighbor Ising action, or nearest neighbor Ising model with some new coupling constants k prime, h prime and e naught prime. So what we are saying is that after this process of integrating out the odd spins, we will get a new Hamiltonian for the degrees of freedom associated with the even spins, and the desideratum or the desire is that we will get the same kind of Ising model but with different coupling constants for the even spins. Okay, and following this we will rescale. Rescale meaning we will change x to x by 2 or x by s generally. So this is the picture that of what I just described. So I'll go through this again. So I'm reorganizing the chain as odd spins and even spins. So I relabel them. All spins are labeled. So for example, if this is a unit cell, the doubled unit cell, this spin is called 2i, and the next one will be 2i plus 1, and this will be 2 times i plus 1 and so on, and this will be 2i plus 3 and so on, right? And this way it goes the other way. So the idea would be to integrate out, and I'll explain to you what that means. Integrate out these red spins. That means you have, in the partition function, you only do the sum over these spins, and you will end up with some kind of effective Hamiltonian for these even spins. And the hope is that it's going to be an Ising Hamiltonian with k prime, h prime and e0 prime. And then I rescale, so that is running x going to x by 2. Then a will become a 2a, this lattice parameter which is now 2a for the even spins, that will become a, and I will restore back my Ising like Hamiltonian. So this is what I would like to do. All this is well and good. This is like proposal if you wish, but can we actually pull this off? That's the question. Okay, so let's go through the first step of decimating or integrating out the odd spins. How can we do this? So now let me write out all the details very carefully. So what I'm going to do is, like I showed in the previous transparency, I am going to divide my lattice into large units, a large doubled unit cell. Each unit cell now contains 2 sites. I will call this as the even site and the odd site. So for example, so like this. So this site is the even site and this is my unit cell containing 2 sites, right? So this is what I have, and what I will do is I'll write the dimensionless Hamiltonian as negative k times. This is the interaction between the 2i plus 1 spin and 2i spin, that is this term here, this thing here. And the next term that I'll show in the next slide is this term, s2i plus 1 and s2 times I plus 1. right? So that's the interaction between those two spins. So each unit cell now has two bonds, if you wish, two links, and that's what this is. And the magnetic field term, we are going to write it as we had done when we were solving the transfer matrix problem by splitting the term in between the links, right? And so it's going to be h by 2 s2i, and everything associated with this, with the central spin of the unit cell, which is this fellow, the red guy, that will of course come with h times s2i plus 1, because that does not have anything going out of the unit cell, and so that's why this factor of 2 is there. And then this is s of 2i plus 1, okay? And in each of these, because there are two sides, the reference energy becomes 2 times easier. So all I've done is reorganize my simple Ising chain into this form where I've doubled the unit cell, and in each unit cell there is an even site and odd site. Okay, all right. Now, if C is a spin configuration, I can think of C as made of the even spin configurations times the odd spin configurations, right? You understand what I mean by times, right? I mean, it means that I can think of the total configuration as configuration of even spins and the configuration of odd spins put together, like some cross product, right? Okay. So what I can do is, the partition function is simply sum over all configurations e to the minus h of c. There is no by t because this is dimensionless, just remember that. And since this h of c is a sum over all unit cells, I can just write it as product over all unit cells and the exponent of whatever is sitting here, right? So that's exactly what that does. Now what I'm going to do is, I'm going to take this sum over all configurations. I'm going to keep the even spin configuration fixed. I will sum that later, and I'm going to sum over the configurations of all the odd spins. So if I look at the exponent here, I can isolate all the odd spins which I'm going to sum over in red color. So there is this piece here, there is that, and there is that. Those are the pieces that are going to get affected by summing over the odd spin configurations. Now you see this remarkably beautiful thing. This is a product over unit cells, and this is sum over all the odd spin configurations. So you see, if I look at what is happening within a unit cell, it is affected only by the odd spin that is sitting at the center of that unit cell. Therefore, this sum over all odd spins can be pushed into the product with keeping the unit cell fixed, and sum over all the configurations of the odd spin. So what I can do is, I have to sum over s2i plus 1 is up and down. And then what will I get is, I'll get a bunch of terms where this s2i, the even spin configuration, is a parameter that is not summed yet, right? That's just outside now. Now what is it that I want to do? I want to just look at this unit cell, and I want to see whether I can convert that to an Ising like interaction between s2i and s2i plus 1. Okay, so this is what I want to check. So the hope is, can this object be converted to an Ising like interaction with a different magnetic field and coupling constant and this base energy between the 2i spin and the 2i plus 1s, the two even spins within the unit cell, with a new magnetic field and a new base, new reference energy. So we are just guessing that this is true. It may be true, it may not be true. We have to check. So how do we check this? So all of you will agree that you can immediately do this sum and get expressions for this, whatever be the value of s2i and s2i plus 1. s2i plus 1. So what I can do is, I can list out the all possible value of s2i and s2i plus 1. So they will be up, 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 down, down, up, down, down. And I can evaluate this on the left side, that is the left hand side, and I can evaluate this on the right hand side, and I can check, can I solve for k prime, h prime and e naught prime uniquely? If I can do that, I am done. Then I know that this identification is exact, and there is an exact solution for that. And believe it or not, you will see that there are three unknowns on the right hand side, k prime, h prime and e naught prime, and apparently there are four equations. Okay, I'll let you work out these equations for yourself. This is an interesting exercise to do. Please do it. You will see that these two equations are the same. So there are only three independent equations for three unknowns, and very interestingly, you can solve them exactly, and we will do that a little later. But for us right now, what we are able to see is that when we decimate meaning when we integrate out the odd spins, the new system that I get keeping the even spin for any even spin configuration is a new Ising system with new coupling constants k prime, h prime and e naught prime. And this is a nearest neighbor Ising model, nearest neighbor now between the even spins. Okay. So that was our first step. So we decimated. Now we rescale. Rescale, what do I have to do? I have to do x equal to x s by s. But now you see what I have done. I had, since I integrated out this, after integrating out, I got this Ising model where my lattice parameter is now 2a. So now if I do x equal to x by s, so what do I have to do? I have to divide all the coordinates by 2. So all of these will just become divided by 2. So I'll get I minus 1 and I plus 1 and so on. And I will rescale my lattice parameter to a. So I have now an Ising model on the same lattice that I start off with the same lattice parameter a, but with different coupling constants. The coupling constants are k prime, h prime and e naught prime. Okay, and this is how I have now implemented my RS transformation. And remember, this is one of the, if you wish, slight downside of these lattice real space methods. You cannot choose an arbitrary S. The natural framework or the natural calculations that will you can perform on such lattices will force you to choose something where s is some kind of integer. In particular, here s equal to 2 is very natural because you can integrate out the odd sides. And so the main upshot of our discussion so far is that if I implement RS for s equal to 2 on the Ising model with the parameters k, h and e naught, I will get a new Ising model on the same lattice with parameters k prime, h prime and e naught prime. Okay. So this is a very, very interesting result. And what we are going to now do is we are going to start with this result. We are going to explicitly work out what is the relation between k and k prime, etc. And we are going to understand what this RG transformation is actually doing. Okay. So just to change the language a little bit. So remember that we used to think of the space of theories. So if you think of space of near neighbor Ising model, the space of those theories, they are characterized by three numbers, namely k, h and e naught. And what we have just shown is that RS for s equal to 2 acting on a point P, which is k, h and e naught, will take it to a new point P prime with k prime, h prime and e naught prime. So there is a small typo here, e naught is missing. Okay. So this is what we have just seen. Okay. Now let's write out those equations that we derived 2 slides back and write them out explicitly. And these are the equations, and I have to solve for these k prime, h prime and e naught prime, etc. Okay, it turns out, okay, with some experience you will realize that these k, h prime and e naught prime are not the natural things to think about here. Instead, we introduce some proxies for those quantities whose transformation look much nicer. So I have something called T. Remember, we had a notion of a little t before, and I will show you that this little t is connected to that little t. This t e to the minus 2k U is e to the minus 2h. So T is the proxy for temperature, U is the proxy for the magnetic field, and V is the proxy for this base, some reference energy. So if you take these equations and just tear them down, if you wish, you will see that if I call the corresponding quantities with k prime, h prime, and e naught prime with the prime notation here, you will see that the renormalization group transformation equations for s equal to 2 read like this. So T prime inverse square, right? So 1 by T prime square is this quantity, right? So if I want to find out what is T prime, I have to calculate this and take 1 by square of that. That will give me what is the T prime after I have done Rs with s equal to 2. And similarly, this is U prime inverse and V prime inverse. Okay. Now, in the context of such lattice methods where S is discrete, these are also called as recurrence relations. They are called renormalization group recurrence relations. Why do we call them recurrence relations? Because suppose I want to do S equal to 4. So this is done for S equal to 2. I want to do S equal to 4. What will I do? I will apply Rs again. So what I have to do is I have to take this T prime that I have calculated after doing Rs equal to 2, stick them back in the same equation with instead of T prime and U prime, I have to, instead of T and U, I have to use T prime and U prime and so on. That will give me, I'll apply these relations twice. And that's why they call it recurrence relations. Now, this is the form of the recurrence relations of this transformation. No? So this is like Rs equal to P going to P prime. So P can now be thought of as T U V, and it goes to T prime U prime V prime given by these expressions. Now let's look at these expressions a bit more carefully. So the first thing we notice is something very, very interesting. So you see T prime and U prime, their new values after the renormalization group transformation has been effected do not depend on the base energy, right? Do not depend on V. So these things transform by among themselves, if you wish, right? So T prime and U prime are the new values will be determined by what are the values of T and U at the previous stage of the renormalization group. V prime is determined by V and these values of T and U and so on, right? So now you will see we have to keep these terms to perform the renormalization group calculation. Why is that? Because suppose I didn't keep this, suppose I did not keep this, I will not have enough equations for the number of unknowns. I get 3 independent equations, I need 3 independent unknowns. So I do need these things to perform the renormalization group calculation. But magically, this base energy does not affect the flow of the temperature and the magnetic field quantities. So what does this affect? So here is the point. The point is that we can simply ignore them because they are going to contribute to the analytical piece of the free energy. So the analytical piece of the free energy, so whatever is being integrated out, you're getting certain constants that has to be absorbed into the analytical piece of the free energy. So we have to keep them, you have to tag them along, but they're not going to affect your results. Okay. So henceforth in this lecture, we are not going to worry about this V term. We'll focus solely on this T prime and U prime terms, TU terms. Okay. All right. So this is the setup. We have now set up the renormalization group equations for Rs equal to 2. Now let's start discussing the physics when there is no external magnetic field. So this is the problem we have solved in multiple different ways in the course. We solved it using just summing the free energy, we then solved it using the transfer matrix method and so on. So before we proceed now, it's a good idea to understand what is the meaning of T and U, which I briefly alluded to in the last slide. So first is T. So remember, T is equal to e to the minus 2k. K itself is the exchange coupling divided by temperature. Now, when T goes to 0, it means temperature is also going to 0. That's because K will go to infinity when temperature goes to 0, and this means that this T will also go to 0 as temperature goes to 0. And when T goes to 1, it means temperature is going to infinity. That's because K is going to 0, and that's where T goes to 1. So little t equal to 0 is 0 temperature, and little t equal to 1 is infinite temperature. In fact, you will be able to see something very nice, that near 0 temperature, recall the exact results. This is not any RG results. This is a result that we derived earlier in the course. This correlation length was the lattice parameter by log cotangent hyperbolic of K. And in the limit t going to 0, you can show that this quantity goes as A by little t. So if you interpret now little t as the distance, the dimensionless distance to the transition, something analogous to T minus Tc by Tc that we have done for the Landau theory, etc., you will see that this nu equal to this correlation length diverging as 1 over T is suggesting that nu equal to plus 1, and this is another motivation for choosing this parameter as the parameter to work with. Right? It gives you a natural, quote unquote, natural notion of a distance to the transition. Okay. Now similarly, U is defined as e to the minus 2 times dimensionless magnetic field, and H equal to 0 will force U equal to 1. Right? As you will see a little later, a more natural quantity to look at is tan H of H, and the reason is H can be taken to be arbitrarily large. So when H is taken to be infinity, you will end up getting tan H is equal to 1, and when H is taken to minus infinity, it will look like tan H is equal to minus 1. So this has some natural advantage. Okay, nonetheless, we will work with the equations with you, but we will make plots using tan H, because that will allow us to see the physics more clearly there. Okay, so now I want to show you the first very interesting result, which is going to teach us something about the renormalization group. Suppose I start with some UV model. UV model means some discrete lattice model, and you have told me what is the value of K, what is the value of H. And you told me that H is 0. You set the external field to be 0. That means U is equal to 1. That's the starting point of the renormalization group. Then, if you just stare back at the equations in the previous slide, you will see that U prime is always 1, right? And T prime inverse is this. So what is this telling us? It is telling us that if I have 0 external field, that means my model has Ising symmetry. The statement is that if you start with a system with Ising symmetry, the renormalization group will produce a new Hamiltonian for you, the scaled Hamiltonian, that will also have Ising symmetry. And that is the statement that U prime equal to 1, which means that it will not generate a new magnetic field. Okay? So the renormalization group transformation will preserve internal symmetries, and in fact this is like a check whether we have done the calculation correctly. If we didn't do the calculation correctly, of course, then you may not get this. Okay, so in the 0 field, we see something very interesting. T prime will be determined only by T, nothing else. Okay. So let's explore what is the meaning of this recurrence relation or the RG transformation rule. Okay. So suppose we start with H is equal to 0, which means that we're going to use that equation, that is, this is our recurrence relations. And let's say I start with T equal to 0.1. Okay. Then for S equal to 2, I apply this once, then T will become 0.2. It will become very close to 0.2. It will not be exactly 0.2, it will become very close to 0.2. When S equal to 4, which means I do this twice, so I take this T equal to 0.2 value and put it back in the equation and compute T prime again, I'll see that it will become 0.38. If I do it 3 times, namely s equal to 8, I will see something like 0.66 and so on. And as I keep doing this, it will start getting closer and closer to 1. So if I keep doing this renormalization group transformation, ultimately this value of t can be made as close to 1 as you want, right? In fact, you will be able to show that this is true for any positive starting value of t. You start with any value of little t between 0 and 1, it will flow to 1 as you keep doing this normalization group transformation. What does this mean? Okay. So recall, at any finite temperature from the exact solution, that there is a finite correlation length c. So, okay, there is a small typo here, the spelling of distance is incorrect. So spins at a distance that are separated by mod x apart, they are correlated as e to the minus mod x by c. Now we know that this is not a generalized homogeneous function, so it will not be invariant under scale transformation. So what will it look like after the scale transformation? After the scale transformation, it will look as if the correlation length has changed from c to c by s, right? That's what it will look like. What does that mean? So after rescaling, the correlation length has become smaller. That means after rescaling, it looks as if the system is at a higher temperature. Remember, correlation length decreases monotonically as temperature increases. So it looks as if the system is at a higher temperature. So the coarse grained system looks warmer, in a manner of speaking, right? So the idea is, suppose someone is doing experiment on some scale at, let's say, 100 Kelvin, and someone else is observing this thing in a coarse grained scale. They are looking at it from a much larger scale. They will say, using the scaled lengths, etc., they will think of the system as if it is a system at a higher temperature. This is the meaning of the fact that T is, as I am running a renormalization group, the T is flowing towards T equal to 1. That means it looks higher and higher temperature, and ultimately if I keep running this RG many times, so I do s equal to 2, s equal to 4, s equal to 8, s equal to 16 and so on, I keep doing this, I will end up going to, the correlation length will ultimately go to 0, which means that I am at infinite temperature where I have completely decoupled spins. So that is the meaning of this statement, that under RG, it's flowing to infinite temperature. Another way of stating this is that there is no critical point at any finite temperature, and there's a finite correlation length at any finite temperature. So it's also in a sense recovering the result that we know from the exact solution, that there is no finite temperature phase transition in the one-dimensional Ising. So the natural question now to ask is, what are the points which are scale invariant, right? So clearly at a point where t is not 0 or 1 or something like this is not scale invariant, because when I do the renormalization group transformation, t will increase. So it's not scale invariant, it's not coming back to itself. The Hamiltonian is not coming back to itself. So what are the points, or what are the values of t for which we can get scale invariance, or let's say what are the fixed points of the renormalization group transformation? So for this, I have to set t prime equal to t and solve this equation. Now if you stare at this equation, you will see it has two solutions. The first solution is what I'll call as T star paramagnetic, corresponds to T star equal to 1. This is the infinite temperature state. And the other state is T star C, which I'll call the critical state, is 0, which is the 0 temperature, 0 field. All of these, if all these are happening at 0 field, please remember that. Right? So these are the two fixed points of the renormalization group transformation at zero field. Okay. So what we can do is we can characterize this by a phase diagram. So the fixed points are the paramagnetic fixed point at infinite temperature. And why is it a fixed point? It's a fixed point because it has zero correlation length. At infinite temperature, all the spins are completely decoupled. There's no correlation length. So if I do the scale transformation, Xi goes to Xi by S, but if Xi is 0, it will come back to itself, right? On the other hand, the 0 temperature state is also a fixed point for a different reason. Xi goes to Xi by S, but if Xi is infinity, remember we have a divergent correlation length as you approach 0 temperature, even then it is invariant under scale transformation, because if you scale infinity by a factor, it will be still infinity. So the moral, a crude model, a moral of this discussion, something to just think about is that fixed points correspond to those systems whose correlation lengths are either vanishing or diverging. Okay. So this is the point that I wanted to make. So these two fixed points, the 0 temperature fixed point has a divergent correlation length, the infinite temperature fixed point has a 0 correlation length, and they are therefore the fixed points of the renormalization group transformation. So this whole story can be summarized in a renormalization group flow diagram. So the points, blue point here is the fixed point at t equal to 0, and the red point is the fixed point at t equal to 1. If you start here, you will stay there because you are fixed point. If you start here, you will stay here because you are fixed point. But if you start anywhere here, you will flow to this fixed point, which is the paramagnetic fixed, infinite temperature paramagnetic fixed point. And we understand why, because you have a finite correlation length, and as you do the scale transformation, under scaling the correlation length will decrease. And you keep decreasing, ultimately you go to 0. That 0 state corresponds to the infinite temperature state. Okay. Now you see something very interesting. So suppose you start with a so you are at this fixed point, but instead of being exactly at that fixed point, you start some tiny bit away from here. Then what will happen? You will flow away from this fixed point. So what do you see? You see the temperature is a relevant operator at the 0 temperature fixed point. On the other hand, if you start not at t star equal to 1, but at some little value of t which is something like 0.99, then under renormalization group transformation you will flow towards 1, which means temperature is an irrelevant operator about the infinite temperature fixed point. Okay, so this is the sort of things that we can work out, and I will encourage you to do some calculations now. I will do a small calculation myself. Okay, so what I'm going to do is I'm going to look at the RG equations near this point, and I will ask you, if I start with t equal to t star c plus delta t, of course t star c is equal to 0, so you can imagine that t itself is delta t, which is a small number. Under renormalization group transformation, you can instantly see it from the previous equation, which is 1 by t prime is equal to 1/2 of 1 by t plus t. You can instantly see that delta t prime will be 2 times delta t. Okay. Now this tells you something very interesting. It tells you that temperature is an eigen operator of the LS, the differential form of the RS transformation. Why is that? Because when I start with something with only temperature, I produce only something with only temperature. So if I put delta t, I produce only a delta t prime. I don't produce anything else. That is what it means to be an eigen operator. Now you see this 2 has shown up here, but our scale factor was 2. What does that tell us? That tells us that this is 2 power mu t, but mu t therefore turns out to be 1. and mu t is 1 means mu t is positive, and therefore it is a relevant operator. Okay. So I went through our previous calculation, and I showed you that I first showed you from the graph that from our flow that temperature is a relevant operator, and then I showed you by a calculation that it is a relevant operator by computing its exponent and showing that it is positive. So I'd urge you to work through what happens around this point. Maybe you can do that later after listening to this lecture. Okay, we worked out what is happening at zero magnetic field. We would now like to work out what is happening at finite magnetic field. Remember, this H is not the physical magnetic field. H is the physical magnetic field divided by temperature. It's the dimensionless magnetic field. Okay, so like we did in the previous case, we should first look at what happens when T equal to 0, right? I am at 0 temperature and I have only H. What will I get? So I will again urge you to take the equations and work them out. We have become a little familiar with the RG equations that the recurrence relations that we developed a couple of slides back. For t equal to 0, you'll get a very interesting result. You'll find that u prime is u square. Okay. So that means if u is greater than 1, under RG it will flow off to infinity, right? On the other hand, if u is less than 1, it will flow off to 0. When u equal to 1, that means there is no magnetic field, it will stay put. But when u is greater than 1, it will flow off to infinity. When u is less than 1, it will flow off to infinity. What is the meaning of this? The meaning of this is that if I have a positive magnetic field, then u will be less than 1. And remember, u is e to the minus 2 times dimensionless magnetic field. So if I have a positive magnetic field, then it will go to, u will go to 0, meaning that the strength of the magnetic field apparently will keep increasing, right? And this is the idea, and it's like so you've taken 2 spins and integrated out, so it's becoming like twice the magnetic field kind of thing, and so it's keeping on increasing. So the natural thing to look at is not, you should not look at u you can use to compute the flow, etc. But the physical thing, nice thing to look at would be tan h. So when u goes to plus infinity, tan h will go to minus 1, and when u goes to 0, tan h will go to plus 1. Okay, and depending on the sign of h, you can work this out. So this is what will happen at 0 temperature. So what is the physics of this? So if I have a small magnetic field at 0 temperature, of course I will get a fully polarized state, right? And it's as if I start with something small h, it will self-generate a magnetic field. Like this is our self-consistent kind of thinking. So everybody, all these spins, because there is J, will produce neighboring magnetic field. So it looks as if there is a finite effective magnetic field at 0 temperature, finite physical magnetic field at 0 temperature, but that finite physical magnetic field at 0 temperature will manifest as a dimensionless magnetic field h of infinity because you are at 0 temperature. So that's what it's saying, that if it's telling you that if I have some external field, it will be a ferromagnet polarized along the direction of that magnetic field. That is the meaning of this result. It's actually fairly straightforward to see. It's yeah, the physics is simple, as I say. If in an external magnetic field, the fully polarized state in the direction of the applied field is the ground state. That is what this is saying. Now let's look at the other end. Suppose I am at infinite temperature. Again, I would urge you to work through the equations. So put T equal to 1 in the recurrence relation and start with any u. Then you will find something spectacular. You will find that u prime is equal to u, and of course T is 1. So T is equal to 1 also will not flow. So you will find that any point of the form T equal to 1 u is a fixed point of the renormalization group. So remember, when we said u equal to u, when u was set to 1, T equal to 1 was a fixed point. We found that u equal to 1 is the 0 magnetic field case. What we are finding here is that u equal to any value other than 1 is also a fixed point of the renormalization group provided T equal to 1. That means if you are at infinite temperature, u will not flow under renormalization group. But here the interpretation has to be done carefully, right? Remember, T equal to 1 corresponds to infinite temperature. So if now H is finite, that means the external magnetic field, the physical magnetic field divided by the physical temperature is finite. That means the external magnetic field is also infinity. So it's a way of taking ratios of two infinite quantities, namely the magnetic applied magnetic field and the temperature. And if you go to infinite temperature, in the sense that the applied magnetic field and the temperature ratio is kept fixed, that H, which determines U as e to the minus 2h, that quantity will not flow under normalization. But that is also easy to understand, because if this ratio is fixed, that means there is a certain population of the up spins and down spins. There is some kind of ensemble of unconnected spins because they're at infinite temperature. But because you have applied these external magnetic field which is also infinite but with a finite ratio with the temperature, the thermal probabilities of up and down spins are going to be determined by these ratios of e to the h and e to the minus h, right? H now being this dimensionless ratio of the infinite magnetic field divided by infinite temperature. So you will get some kind of paramagnetic state. Each paramagnetic state has a different thermal weight of the up and down spins, different statistical weight I should say, and they are not coupled to each other in the sense that since temperature is empty, J has no effect and therefore a zero correlation length and therefore scale invariant. And this is the origin of the line of fixed points now. The line of fixed points, because t equal to 1, any value of u or any value of tan h between minus 1 and plus 1 is a fixed point. Okay. So this is the set of all paramagnetic states you can get in the system. Okay. So with all this discovered, we can now summarize this whole story in the full renormalization group phase diagram, where I have plotted as a function of t along this axis, and instead of u I use tan h because this is a much more physical thing to think about. Let me first visit all the points which we have already studied. So this is h is equal to 0, namely u equal to 1 and t equal to 0. This is our 0 temperature critical point. This point is the fully magnetized state, if you wish, right? The state with all spins up, and this is the state with all spins down, right? They are fixed points. And this line corresponds to infinite temperature, and this is a line of fixed points. Line of fixed points. Each one of these have zero correlation length, and if you do scale transformation, they will come back to themselves. Okay. So now let's see what is the flow like, right? So if I start here, and if I am along this line, that means I am zero magnetic field, and this is the line that I showed you 2 slides back in the h is equal to 0 discussion. So what happens here is, you see, if you look at this fixed point, you see that if you are away from this fixed point in any direction, you will flow away. That means that you have 2 relevant directions at these fixed points. There is the temperature is a relevant direction, as well as this magnetic field is a relevant direction. If you look at any fixed point here, it has no relevant direction. This direction in this story is a marginal direction, because you see, if I am here, I will not flow in that direction. But if I am here, I will flow into this. So this is an irrelevant direction. Okay. So now the point I want to say is, the interesting critical properties that we are interested in are near this critical point, which is the critical point at 0 temperature and 0 magnetic field. And this is the most interesting critical point we would like to study. Okay. This whole t equal to infinity set of critical points kind of trivial, we understand it, it's just the paramagnetic phase. So why do I call it a phase? I will discuss this later after discussing several other examples. Okay, so we have set up everything for us to do our first calculation of critical exponents from renormalization group, not from exact calculation, from renormalization group. Okay. So let's go to this 0 temperature, 0 field fixed point, which is this point here, and let us work out what are the RG equations near this point. Remember, U star C equal to 1 and T star C equal to 0. So I would encourage you to work this out. If you work this out, you will see that delta T prime and delta U prime are related to delta T and delta U in this fashion. So first observation is that both delta T and delta U are eigen operators of the LS, the differential transformation associated with RS. And this is now telling, because our scale factor S is equal to 2, we are seeing that mu T equal to 1 and mu H is equal to 1. Now I have got mu T and mu H equal to 1, which is all I need to compute all the critical exponents from the scaling hypothesis, which is no longer a hypothesis. Scaling, the fact that it's a generalized homogeneous function is given to us. So if I know mu T and mu H, I can compute all the other exponents, and this is what I'm going to do now. Right? So using scaling laws and all the stuff that we have seen, alpha is 2 minus 1 by mu T, which is 1, beta is equal to 0, gamma equal to 1, delta inverse is turning out to be 0, nu turns out to be 1, and this is from the hyperscaling. I have used the spatial dimension d equal to 1 explicitly here, right? And from the Fisher law, I am able to get eta equal to 1, right? And we recover all the known exact results of the exponents from renormalization group. In a sense, I did not solve the Ising model I didn't compute any full partition function or anything. All I did was how the coupling constant evolve upon scaling and explore those in the vicinity of those points which are fixed points of the renormalization group transformation, and from there I am able to pull out these critical exponents. So I hope you will appreciate that this is definitely a non-trivial exercise, and it is something very instructive, in the sense that we have seen a framework in which we can start from some UV model, UV meaning discussed in terms of the microscopic degrees of freedom, and we are able to come up with a scheme to claim or a way to compute these critical exponents, explain scaling, all of this stuff within this framework, and it requires only one important principle, which is that at these critical points or at fixed points, the system picks up a scale invariance. So that is the main idea that goes into finding these results. Okay, so let me summarize this lecture now. So the real space methods that we have studied for the Ising model involve two steps. So we first decimate and integrate out some set of degrees of freedom, and then we rescale, and we use this idea in the 1D Ising chain to get RS equal to 2. And this, I must at this point of time tell you, is one of the somewhat of not a very attractive feature of these real space methods, because you cannot choose any S you like, right? You have to go with certain S's that are nice and compatible with the lattice, so that you can actually do some calculations. In most instances, it turns out to be enough if you know a single S, because then you can keep scaling and you can find things. But you would also like to have the wherewithal to do arbitrary S, which is of course more easily done in the Wilsonian framework, as we'll see. And this renormalization group framework recovers all the exact results that we know. In particular, it shows that there is no finite temperature transition in the 1D Ising model, and we have also found a way to compute the critical exponents. So what's coming up next? So the natural question is the famous two-dimensional Ising model, for which also we know the exact result and exact exponents. What can we do with this real space method for the two-dimensional Ising model? Can we recover the exact results or no? I'm sure you will want to know this. So I'll see you in the next lecture. Have a nice day. Thank you.